Good afternoon, everybody. As you can see, there's a do now. This will help shake the cobwebs off and remind you what we were doing last week before you had your exam. We'll wait another 5 minutes to give people a chance to roll in, try the do now, and then I'll start going over it. If you have any questions, feel free to post it in the chat. Good afternoon again. We'll get started with the do now. Given the following decomposition reaction, calculate the moles of oxygen gas produced from 5 moles of hydrogen peroxide. So this question requires you to write a mole-mole ratio. If you have an answer, you can go ahead and put it in the chat. If you're stuck or you're like, I don't remember this, then you can go ahead and let me know that too. That'll help me as we go along. So we're trying to figure out how many moles of oxygen gas we produce. Uh-oh. There we go. So we need to have a mole ratio that talks about hydrogen peroxide and oxygen gas. For the mole-mole ratio, we can write 2 of them. And this is just taking the number of moles of each compound that we're interested in the chemical equation and writing it as a fraction. We care about the relationship between the hydrogen peroxide and the oxygen gas. So that's what we're going to write about. In the balanced equation, there's 2 moles of hydrogen peroxide and 1 mole of oxygen gas produced. We can write the reciprocal of that with the 1 mole of oxygen gas on top. So these are our 2 mole ratios that we have to choose from. If we're trying to figure out how much oxygen we make, which one should I use? Whitney already put it in there, but let's let everybody else join. We need to use the second one. We need to use B. And when you do the math, you should get 2.50 moles of oxygen gas. So that's a refresher for writing the mole ratios. That's really the centerpiece of all the different stoichiometry problems that we did last week and the ones we're going to continue with this week. Are there questions on that? I'll take that as a no. So we're finishing up Chapter 9 this week. We went over a couple of stoichiometry problem types last week. We'll do a recap for both of those, and then we'll jump right in. So I will do these out for you, and I'll ask you some questions along the way. I'd encourage you to kind of look at your notes and make sure that it's at least jogging your memory and it's a little bit familiar. And then we'll be in good shape for finishing up Chapter 9. This first question, what is the mass of zinc oxide that can be prepared from 1 gram of zinc metal? We talked about identifying the problem type before you start solving anything. We're given a mass of 1 gram of zinc. We're asked about a mass of zinc oxide. That makes this a mass-to-mass problem. The way that we solve mass-to-mass stoichiometry problems is this, and this is the generic form. Starting with your grams of A, you have to get to moles. You need the molar mass to do that. To go from moles of A, which is our given, to moles of B, what we're interested in, we need a mole-mole ratio. And that's going to take the form of B over A directly from the chemical equation. The last piece is converting those moles to grams. Again, we're using a molar mass, but this time it's the molar mass of B. To put this into perspective, the A in our generic solving plan is zinc, and B is the zinc oxide. So I'll write out our plan with these two things in mind. And feel free to work ahead of me and solve the problem and put your answer in the chat. If you're like, Dr. Hefner, I got this. Here's the answer. I'm not going to hold you. Go for the gold. But for anybody who needs that refresher or just needs some extra help, this is for you. So we're going to convert the grams of zinc to moles of zinc using the molar mass, which I will list here. Then we take those moles of zinc and convert to moles of zinc oxide. For that, we need a ratio of B over A, which is zinc oxide over zinc, directly from the chemical equation. We convert those moles to grams using the molar mass of zinc oxide. So that's our plan for solving this. How are we doing so far? Is this ringing a bell? Does it look familiar? Good. Now it's time to fill in some numbers. We're starting with 1 gram of zinc. For our molar mass, we need to go from grams to moles. So am I putting the grams in the top or the bottom? Yep, I'm putting them in the bottom. Now I need a mole-mole ratio. And I'm looking at the zinc oxide and the zinc. What is my ratio going to be? It's going to be 2 to 2. Two moles of zinc oxide for every 2 moles of zinc. No, you're good. The last part, we're using the molar mass of zinc oxide to get to grams. Grams are going to go on top this time. When we cancel all of these units out, we should be able to follow along with our plan. We're starting with grams and converting to moles of zinc. And that's what we said our first step would be. Then we use the mole-to-mole ratio to get the moles of zinc oxide. And that's our second step. Finally, we use the molar mass of zinc oxide to get to the grams, which is what we want at the end. If you do all the math, you should get 1.24 grams. And don't forget, if you see a number in the denominator, which is the bottom, you need to divide. When it comes to the mole ratio, sometimes you have to multiply and then divide. So if it's not, 2 to 2 or 1 to 1, you need to multiply and then divide. Any questions on this? Yes. Nah, you good. Because it all depends on the molar mass that you use. It all depends on the periodic table that you use. So you would be fine for me. You're welcome. So that's mass to mass. That's a recap. We also did mass to volume. So we'll use the same equation, but this time we're trying to find the volume of oxygen gas that we need to fully react with that 1 gram of zinc metal. Since we're talking about a mass and a volume, it's got to be a mass to volume question. Don't skip that step, because when you're in the thick of it and you're trying to do homework problems or a quiz, your exam, you don't want to pull out the wrong thing. You don't want to pull out the wrong formula for solving the problem. I'll give you the generic form, and then I'll write in our plan using the zinc and the oxygen. The goal of the first step is always to get to moles. Oops, I lied. There. So our plan is always to get to moles first. From whatever we're given, if it's not already in moles, we have to get to moles. So we use the molar mass just like we do last time with the mass-to-mass question. Then we have to get from moles of A, which is what we have, to moles of B, what we want. That's going to be our ratio. That's always the connecting piece, to go from what we're given to what the question is asking for. And in these problems, it's always going to be what you are looking for, what's in the question, the B, over A for your ratio. But this time we're trying to get to liters. That's the volume of a gas. So we have to use molar volume here. The question says that we're at STP. So we can use molar volume to convert from moles to liters. Remember that 1 mole of gas is equal to 22.4 liters of gas. We're going to use that unit equation to write a unit factor that will convert the moles to liters. Now let's put our plan into more specific terms. Zinc is our A, oxygen gas is our B. So we've got moles of zinc. We get to moles of oxygen gas using that ratio. So always remember to assign your A and B, and that'll make finding the mole ratio a lot easier. So feel free to work ahead if you got it, and put your answer in the chat if you want to. Otherwise, you can work along with me. We're starting with our zinc. This is going to look exactly the same for this first step. For our mole ratio, we're looking for the oxygen, which is 1 mole, directly from our equation, over zinc, which is 2 moles. That's our mole-mole ratio. For the last piece, we have to write a unit factor from our unit equation. The unit factors look like fractions. For this, we're trying to get rid of moles and be left with liters. To cancel out the moles, we need moles on the bottom. So if we're doing mass to volume, you'll always use 22.4 liters on top and 1 mole of your gas on the bottom. When we're canceling the units, we can follow along with our plan. We went to moles of zinc, then moles of oxygen, then liters of oxygen. And if you do the math, that's what you should get. And again, the last digit I'm not going to be too strict on, but you can't tell me 0.2, okay? That's the recap from mass to volume. Any questions here? I'm going to assume that's a no. Try your calculator again. That'll do it. But on an exam for me, if you're that close and I see that you wrote it all out right, you'll get full credit. I'm not going to hold you for that, okay? The procedure is what's most important. Okay. So we left off with volume to mass. And I did this example for you last time, but I'm going to run through it again just to make sure we're all on the same page. And then I'll let you loose to do your own problem, a volume to mass problem. How many grams of sodium chlorate are needed to produce 9.21 liters of oxygen gas at STP? We're given a volume. And we're asked about how many grams. So that makes this volume to mass. It's going to be the same thing that we just did, only in reverse. You're starting with liters, and you need to get to moles. This is going to be with molar volume. The centerpiece is always going to be that mole-mole ratio, because that's how we can convert from one substance to another in a chemical reaction. Then you can convert to grams using the molar mass. In this case, what we're given is liters of oxygen gas. So oxygen is going to be A. We're trying to figure out the grams of sodium chlorate. So sodium chlorate will be B. So I'm going to write this out here real quick. Remember our equality, or our unit equation. Sorry, thinking in another textbook lingo. Same thing. So that's our unit equation. For the mole-to-mole ratio, it's going to be the sodium chlorate over oxygen gas, directly from the chemical equation. And the molar mass that I used is right there. Now let's work out the problem. So last time we had the liters on top for our molar volume unit factor. This time we're going to put liters in the bottom because we want to have moles and cancel out those liters. So that's always going to be the unit factor here. 1 mole over 22.4 liters for volume to mass. When we look at the equation, we've got 2 moles of sodium chlorate and 3 moles of oxygen gas. So remember, when you're doing this in your calculator, you got to multiply by 2 and divide by 3. I see that mistake quite often. Last, you need your molar mass. So you should get 29.2 grams. Any questions on that? So we did this one last time, but it was at the end of class, and sometimes that just gets pushed out of your brain. So are we ready to try a volume to mass problem? So here you go. This time you're trying to figure out how much sodium chloride, so this guy, is produced when you make 9.21 liters of oxygen gas. I'll give you 5 minutes to get started. You can put your answer in the chat if you get to an answer. But after about 5 minutes, I'll start going over it. I'll go ahead and start setting up the plan. And you can keep on working and put your answer in if you're working towards an answer. So if you got stuck, there's the plan. Let's fill in our numbers here. What's our mole ratio going to be? It's going to be 2 to 3. For those of you who are not participating in the chat, let me know that you're still with me. And if you have a question, it's really okay to ask. You pay tuition too. So with sig figs, it's 16.0 grams. So several of you got that answer, which makes me happy. If you didn't get there, hopefully the plan helped you out a little bit. But also practice. I'll be sure to post some practice problems in the Chapter 9 folder. And you can practice on those and have the answer key. So you can kind of compare what you're doing to what I did, and you can see where you're making your mistakes. So how do we feel about these volume to mass problems? Go for it. You would want to convert milliliters to liters if you're given a volume in milliliters, because molar volume is 1 liter per 1 mole is equal to 22.4 liters. So your units have to match. You're welcome. Yeah, on mastering chemistry, that's definitely something you want to look out for. Make sure that when you're doing volume problems, that you're using liters, not milliliters. So we covered the first two types, mass to mass and mass to volume. We threw in the bonus of volume to mass, which is just the reverse. Now we're going to do volume to volume, which is the easiest. With volume to volume problems, we're making the assumption that everything is in a gaseous state and it's all at the same temperature and the same pressure. So you'll see something like at STP or at the same temperature and pressure or something like that when you're doing mastering chemistry or if you're doing an exam question. And what we can assume here is these coefficients, the 2, the 1, the 2, we can say moles, but we can also say liters if we're talking about all gases. So when the question asks how many liters of oxygen react with 37.5 liters of sulfur dioxide in the production of sulfur trioxide gas, we only have one step. You're going to take the liters, somebody's mic is still on. We're going to take the liters of our first gas, the given, and convert to the liters of what we're looking for, B, using a ratio. We'll call it a mole to mole ratio, but it's really like a volume to volume ratio. And that's it. So in this case, we're starting with liters of sulfur dioxide gas. And make sure you get your names right from chapter 6, because we've got sulfur dioxide, sulfur trioxide. You need to get that naming down. We're trying to figure out liters of oxygen gas. For our mole-mole ratio, that means oxygen gas over sulfur dioxide. That's where we're starting our given information. We're using the chemical equation still, but instead of writing moles, we write liters. So when you do your division, you should get, with rounding and sig figs, 18.8 liters of oxygen gas. Any questions on that? I told you this one was easy. I'm going to take that as a no. No questions. Yeah. No, I promise it was easy. So now I want you to try one. How many liters of sulfur trioxide gas are produced from 37.5 liters of sulfur dioxide gas? So we're looking at these two. I'll give you a minute to set it up, but you probably won't even need your calculator once you set it up. You can put your answer in the chat. I'll start setting up the problem. So our mole-mole ratio here is 2 to 2. That makes the math pretty easy. So you should get 37.5 liters. Kind of anticlimactic after doing the other two types of problems, but I'm sure it's a relief. Any questions here? Oh goodness, yes. SO3, thank you. So I have another example here. It seems like y'all are good, so let me know if you want to try this one or if you want to move on. Okay, that's what I figured. So this would be a good time for a break. We've only been in class for almost an hour, but the last two concepts are kind of related. So why don't we take a few minutes? We'll take a break until 3 o'clock, and then we'll get started again. All right, y'all, it's 3 o'clock. We're going to get started again. We went over 3 types of stoichiometry problems: mass to mass, mass to volume, and volume to volume. We can build on those concepts and combine it with other problem types. The first concept I'm going to introduce is the limiting reactant concept. So let's step out of the chemistry lab and step into the kitchen, because that's like my favorite place. Love to cook. And hopefully you've had lunch by now. Let's say you're making grilled cheese sandwiches. If you're going to make just the most basic grilled cheese sandwich, you need a couple of slices of bread, a couple of slices of cheese. If you write that as a reaction, it's 2 slices of cheese plus 2 slices of bread gives you 1 sandwich. If I had 2 slices of cheese and 10 slices of bread, I can still only make 1 sandwich, because I've only got enough cheese for 1 sandwich. The rest of that bread is in excess. The cheese is limiting. The bread is in excess. Does that concept make sense? We got a not really and a yes. So let's run it back one more time. Let's say we're making brownies and you have a box mix, right? If the box mix says to use 2 eggs, and you have in your fridge, let's say 4 eggs. Oh, yeah. Yeah, it's an example. It's just an example. I was going to give you a whole different analogy. But if you have 2 slices of cheese and 10 slices of bread in your home, you can only make 1 sandwich. Okay, good. Praise them. Because I was like, the brownie one's going to be a little bit more complicated, but it might work. We can apply that same thinking to a chemical reaction. Oftentimes in the real world, you're going to have a limiting reactant, and that controls the amount of product that you make. Uh-oh. Well, we're going to go over it again, only talking about chemicals this time. So, in the real world, sometimes one of the reactants that you need is really expensive, or it's very rare, and that's going to limit how much product you make. So the limiting reactant is the one that's used up before everything else. All the other reactants are present in excess. Let me show you what I mean with a simple problem. We have 5 moles of iron and 3 moles of sulfur. These are both reactants. And we're asked about how many moles of iron 2 sulfide are formed. And the reaction is below. What we're really doing here is saying, okay, if I have 5 moles of iron and 3 moles of sulfur, which one is going to run out first? The iron or the sulfur? The way we figure this out is by doing 2 small problems. The first one would be to take that iron and say, if I had all the sulfur in the world, how much iron 2 sulfide would I make? We know how to do that. That's pretty easy. You take your 5 moles of iron. You write a mole-mole ratio between the iron and the iron 2 sulfide. It's 1:1. So if you have 5 moles of iron, you make 5 moles of iron 2 sulfide. But we can't ignore the sulfur. We're told about the sulfur too. If we had 3 moles of sulfur and all the iron in the world, how many moles of iron 2 sulfide would we make? Same deal. You use a mole-mole ratio, and it's 1:1 as well. Oops. That should be iron 2 sulfide. So these are the 2 small problems that we have to do to figure out how much product we would make if we only had 5 moles of iron, and how much we would make if we only had 3 moles of sulfur. Now we need to compare the 2. The question you have to ask yourself is, which reactant makes the least amount of product? We've got 5 moles of iron 2 sulfide versus 3 moles is smaller. That's the least amount of product. So that's what we're going to form, which means sulfur is limiting. So talk to me. Does that process make sense? Can you say that again? My volume was a little low. You always have to do the math because it's not based on the amount, it's based on the mole-mole ratio. Here, the mole-mole ratio is 1 to 1. So the amount of sulfur is the amount of iron 2 sulfide. But if it was 2 to 3 or 3 to 2 or something like that, you don't know until you calculate it. Other questions? This is the basic concept of determining a limiting reactant. From here, we're going to build and incorporate the stoichiometry problems we were doing with the limiting reactant concept. So if this slide don't make sense, then everything else is going to be a wash. So let me know if you're with me. All right, we're going to go ahead. So this is an example of a limiting reactant problem that's coupled with the stoichiometry problem. This is the example that I did in the YouTube video, and I'm going to do it again here, and you'll have the opportunity to practice. How much molten iron is formed from the reaction of 25 grams of iron 2 oxide and 25 grams of aluminum? And we have the reaction below. Whenever you're given two reactants in two different amounts, that should clue you in that you're doing a limiting reactant problem. We're given grams of iron, or iron 2 oxide, and grams of aluminum. And we're trying to figure out, if we mix these two, how much molten iron will we make? So this is combining mass to mass and limiting reactant, which I abbreviate LR. We're going to end up doing two mass to mass type calculations and then comparing the two to figure out how much molten iron we actually make. For the first one, we're going to look at the 25 grams of iron 2 oxide and figure out how many grams of molten iron we can make. I'm not going to write out the plans for these. I'm just going to write out the equation. The first step is always getting to moles. To go from grams to moles, you have to use molar mass. The second step, we have to figure out our mole-mole ratio. Our B is the iron, so that means the moles of iron from the equation go on top, and the moles of iron 2 oxide go on the bottom. Last, we use the molar mass of iron to get to grams. When you do all that math, you should get 19.4 grams of iron. Now we have to do that again. Only this time it's with 25 grams of aluminum. It's the same exact thing, only this time we're using the molar mass of aluminum. And we're using the mole ratio between iron and aluminum. The iron still goes on top, and that's 3 moles directly from the equation. We have 2 in front of the aluminum, so that's what we put in the bottom. The last step is still going to be the same because we're converting the moles of iron to grams of iron. And you should get 77.6 grams of iron. But we're not done. We have to decide whether we're making 19.4 grams or 77.6. If we use the iron 2 oxide number, we'll make the least amount of product. So that's how much we make. And iron 2 oxide is limiting. So talk to me. Does that process make sense? Okay. So the first thing we had to do is figure out how much we would make from each reactant. If we said, okay, you have 25 grams of iron 2 oxide, go. How much iron are you going to make? Then you say, if I have 25 grams of aluminum, how much iron am I going to make? Then you compare the two. How much iron do I get from the iron 2 oxide? How much do I get from the aluminum? Whichever one is smaller, that's the amount you actually make. Right. So I moved through doing the calculations a little bit fast, just because we've done the mass to mass a few times. But if you have questions on that, or if you want me to slow down, I can. It's still the same concept as the previous slide, where we figured out how much of the product we would make using both of the reactants and then compare. Do you want to try one on your own, or do we need to go over this one again? Yeah. Okay, that's fine. So we'll kind of do this one together, okay? So I'll give you some parts, y'all fill in some parts. we still have the same equation. This time we're looking at aluminum oxide. If we have 25 grams of iron 2 oxide and 25 grams of aluminum, and we're mixing them together, how much aluminum oxide will we make? It's still mass to mass and limiting reactant. The first thing you have to do is figure out how much aluminum oxide you would make if you had 25 grams of iron. So I'll give you a couple of minutes to just solve that problem. Oh, and that should be iron oxide. Iron 2 oxide, not just iron. So figure out that mass to mass problem first. And you can put your answer in the chat. If you're feeling lucky and you're done before everybody else, then you can move on to the second part of the question, which is if you had 25 grams of aluminum, how much aluminum oxide would you make? So I'll check in after 2 minutes or so and start filling in the first part. Then I'll give you another couple of minutes and fill in the second part. If you have questions in the meantime or you get stuck, you can ask or put it in the chat. I'll start writing out the equation for the first one, but keep on working and you can put your answers in the chat, or you can just keep going through the whole problem. Completely up to you. So for the first part, you should get 11.8 grams of aluminum oxide. I'll give you another minute or so, and I'll put in the equation for the second part. I'll start writing up the second part. When you do the math, you should get 47.2 grams of aluminum oxide. But we're not done yet. We still have to determine how much we're actually going to make by mixing these two together. We have to make the least amount of product. That means we're going to make the 11.8 grams. And iron 2 oxide is again limiting. Which you probably could have guessed, but you still needed to do the math to figure out how much. So how do we feel about this one? Did it help to Leah to kind of break it down step by step instead of saying just go for it? Good. Okay. I didn't want to just leave you hanging there. We did this for you, girl. Mm-hmm. Yes. Good. You're welcome. Let's try one more. This time, it's a volume to volume question along with limiting reactant. I'm going to let you try it. I'll give you 5 minutes. Oh yeah, I can go back. But when I go forward, I'll give you 5 minutes to go through the whole process yourself. So you'll do 2 volume to volume questions, and then whichever one makes the least amount, the smallest amount, that's how much you'll make. So 5 minutes. You can put your answer in the chat or just wait for me to throw it up. Y'all are great. Y'all gonna be great. Just don't forget me. Just send me a few pennies when y'all make it. Send me a picture. Sign it. All right. So let's get this problem done. Like I said, it's volume to volume. Yeah, you're welcome. It gives me great joy to do this with you guys. It really does. And that's saying something because I like my family a lot. So, y'all are real ones. Y'all are some real good ones. You're welcome. I am full of gratitude. This is my pouring out to you. I'm sure you don't hear it a lot, but thank you. It takes participation to be a good instructor. It can't just be a one-way street. So I'm always grateful when there's participation. So we have to solve 2 problems just like all the other limiting reactant problems. Only it's not going to be as much work this time because it's volume to volume. we remember from last time that 2 to 2 is our ratio. So however much sulfur dioxide gas you have, that's how much of sulfur trioxide gas you'll make. However, we didn't do the one for oxygen. That was the sample or the example problem that we skipped over because y'all were pretty much good. The ratio for that, we're still going to have the 2 liters of sulfur trioxide in the top, but we only need 1 liter of oxygen gas to make that. So if we had 18 liters of oxygen gas, we would make 36 liters of the sulfur trioxide gas. Now we have a decision to make. We have to choose the one that makes the least amount of product, so the smallest number. That's the 18 liters, which means the sulfur dioxide is limiting. So how do we feel about that one? All right. One last concept and then we're done. So we will very likely finish early. We're doing all these stoichiometry problems, and we're calculating how much of a product we'd make if we had X amount, Y amount, blah, blah, blah. But in the real world, it's never that pretty. I'll tell you that from first-hand experience. When you're doing an experiment, you never make the amount of product that you think you're going to make. So when you're performing an experiment in the lab, the amount of product that you collect is the actual yield. The amount of product that you calculate is the theoretical yield. So all of the limiting reactant problems, the stoichiometry problems that we've been doing, like the mass to mass and mass to volume and all those are theoretical. The percent yield is calculated by taking a ratio of the actual yield divided by the theoretical yield and multiplying by 100%. In most problems, the actual yield will be given. There's nothing you can really do to figure it out. So if the question is asking you about percent yield, one of the numbers is going to be the actual yield from the experiment. The theoretical yield might be given to you directly, X number of grams, or you have to do one of those stoichiometry problem types to calculate the theoretical yield. So I'm going to go through an example of the simpler way first, which is you have both the actual and theoretical yields, and you just have to calculate the percent yield. So let's say a student performs a reaction and you obtain 0.875 grams of copper-2 carbonate, and the theoretical yield is 0.988 grams. What is the percent yield? We said To calculate that, I think somebody's mic is still on. To calculate that, we take the actual divided by theoretical, multiplied by 100%. The actual yield is 0.875 grams. They perform a reaction and obtain. So that tells you that's what they got in the real world. And it spells it out plain as day that the theoretical yield is 0.988. When you do that math, you're just going to take the 0.875 divided by 0.988 and multiply by 100%. With sig figs, you should get 88.6. Does that make sense? So now we're at a crossroads. We've got two options. We can do an example just like this one, and you can practice percent yield. Or we can move on to the more complex problem where we do a stoichiometry problem first to calculate the theoretical yield. And then we can calculate percent yield from there. So easy problem or hard problem. We're going to do the hard problem either way. So if you want to jump to the hard one, let me know. Alright. That's kind of what I figured. So I'll make sure to put the answer to this one in the notes before I upload it. So I'm going to let you guys do this one. I'm going to help you get set up, and then I want you to try it. So you're taking 10.5 grams of iron 2 oxide with excess aluminum, and you get 6.25 grams of iron. You have to figure out what the percent yield is. The 6.25 grams, that's your actual yield. The 10.5 grams of iron 2 oxide, that's what you started with. You have to figure out how many grams of iron you would theoretically make if you were to do this. That means you have to do a mass-to-mass problem to figure out the theoretical yield. Once you do that, you can plug it into the equation for the percent yield and get your answer. So I'll give you 5 minutes to get started on that. Then I'll start writing things out. If you get stuck or you have a question, just let me know. I'm going to start setting up the mass-to-mass problem. I'm not going to write out the plan, but I'll write out the equation and the color coding. So that's the first part. We figured out the theoretical yield. For percent yield, we need actual over theoretical, and we multiply that by 100%. The actual was given in the problem, 6.25 grams. We calculated the theoretical, 8.16 grams. You multiply by 100%, and you get 76.6%. So yes, you're right. Questions on this? 5 minutes is not a whole lot of time to do the whole problem. So if you didn't finish, that's okay. But does the concept at least make sense? That's all I have for you. That's the rest of Chapter 9. So remember, there's no office hours this week. After this class is over, I'll make sure to post all this on YouTube, get all the notes and everything up, get practice problems up, and then I am taking off the Dr. Hefner hat and putting on the mama hat. Be with my family. So if you have an emergency or in a crisis, I can't do anything anyway. But if you send me a message or something like that, I won't see it. If you get it in before like 4:30, I'll see it. Otherwise, I'm not going to see it until Monday. You don't have any chapter check-in due this weekend. Your mastering chemistry isn't due until November 15th for Chapter 9. I do want to remind you about the final exam. So that schedule is up if you haven't looked at it yet. We're slated to have our final exam on Tuesday, December 8th from 2 to 4 p.m. I know you're accustomed to having multiple days to do the exam. For the final, that's not the case. You will need to start the final in the window of 2 to 4 p.m. and you'll have 2 hours to complete it. So if you work sometimes, or you know somebody who's not here who's, like, oh, well, I'm going to just work and then watch it on YouTube, make sure they know. Don't work on Tuesday, December 8th from 2 to 4 p.m. because you will not be able to access your final exam outside of that. We just have one more chapter to go, and that's Chapter 10 on gases, which we will do starting next week. We may be able to finish it in 1 week, depending on how it goes, but it's scheduled to be over the course of 2 weeks. So if we finish early, we can either do final exam review for the last class, or we can make it optional and y'all can just not have class. So we'll talk about it next week when we come back to class. That's all I have for you. If you have any questions, feel free to ask now. Or you got an extra 35 minutes in your day. So clap, clap, praise them, do your dance, and enjoy yourself. Try to get a little bit of sunshine. Let me know if you need anything. So you have to go on to the main website, and then I have to think about it for a second. You have to go to because I have my links already built in. Is it this one? I'm literally on the website like right now. No, it's. Oh, you know what? I think it's Is it academic resources? Because there's a separate page that I go to for faculty stuff. And I know that if you go there, you'll find it. Information for faculty and staff. And then I just go to academic calendar and exam schedule. You can do that. And actually, I can toss the link. There we go. Let me copy it. So that's the link that I use.